Hi, my name is Chris Dewy, and today I'll be presenting my implementation on deep Q networks. The motivation for this project was Google DeepMind's work on reinforcement learning. A recent example of DeepMind's work in the space is their AlphaFold 2 algorithm, which was able to predict protein structures with near experimental accuracy. As you can see, these models can be really impactful in real-world circumstances. The paper I chose to re-implement was Playing FPS Games with Deep Reinforcement Learning by Lampel and Chaplot. They used a deep Q network trained agent to exceed the performance of human players in the 1993 game Doom. I wanted to use some of their model tricks to see if I could improve performance compared to a naive deep Q network. I did my implementation using the GIM platform and the cartpole v1 environment. So to explain what a DQN algorithm does, it iteratively trains an agent to maximize rewards in its environment. In this case, the environment is going to be a video game. The agent chooses actions which affect the state of the environment, and it receives a positive or negative reward for doing so. The inputs are the current state space and possible actions, and the agent chooses from those possible actions. The agent can either explore the state space by taking a random action, or it can choose an action by predicting which one will receive the best reward based on prior learning. We use an epsilon greedy policy such that the agent explores with probability epsilon and otherwise predicts from prior learning. We start with epsilon equals 1 since the agent starts knowing nothing and needs to explore the space 100% of the time. But over enough time steps, we decrease our epsilon to 0.01 because we assume that the agent has learned significantly. We always explore a little bit because we assume the agent's never perfect. The brain of our algorithm is a neural network that attempts to optimize for cumulative rewards according to the Bellman equation. Basically what that means is the actions our agent chooses should maximize the cumulative discounted rewards. Now, we have to discount future rewards by a gamma value because by valuing our early rewards more than later rewards, we're facilitating an early model convergence. And this can be really helpful when training RL algorithms because they can be so tricky to converge. Now, deep Q networks are really sensitive to hyperparameters. For our project, I tuned learn rate and gamma myself, and as you can see, especially with our chart of gamma, the average reward over the last 100 state steps is vastly higher for our gamma equals 0.7 compared to all other values I tested. So this one hyperparameter value performs really well while the others perform quite poorly. So this just helps to show you how much of a challenge it can be to tune the hyperparameters for DQN. For my naive implementation, I did 300 training iterations. Now you can see the model performance in purple, which is the average reward over the last 100 time steps. Now, our naive model solves cartpole in around 135 iterations, but this solution diverges after 240 iterations, so it's not a stable model. To try and improve our model, I added some tricks from the researcher's paper. But just to show you what this actually looks like when you have a trained model. So on the right, this is our model that's been trained fully with the naive DQN, whereas on the left, it's showing what the model does when we're exploring 100% of the time or choosing random actions. Now, the goal of this game is to push the cart left or right to keep the pole upright. As you can see, the trained agent does much better. The first performance improvement that I tried to go for was by including memory delay. So memory delay prevents early model updates by forcing the model to wait until 100 states have been passed before it starts updating the neural network. At this point, you can pull from that entire memory of 1,000 actions and the rewards, and so this helps prevent training your model with error at the beginning just because you don't have enough data. As you can see, this made the model perform significantly better with having a solution at around 220 iterations, and it stays converged. The second piece of the researcher's paper that I implemented was frame skip. The idea behind frame skip is that humans aren't going to be updating their knowledge every single frame or every single state. So presumably, we can have our model wait a few states before it updates the neural network. For my model, I waited 5 states in between updating the neural networks. And naturally, this takes a longer time to converge, but ultimately, this is able to solve cartpole in only 160 model updates compared to 220 model updates from the patient model. This is the most robust model of the 3. So in conclusion, Our results were quite good. The models performed better with the memory delay and then frame skip applied, as would be expected. So, the more tricks we added from the researcher's paper, the better the performance. But I would have liked to have been able to add a few more bits from the researcher's paper, such as doing a convolutional neural network solution using an image input, and also applying my models to a more advanced environment so I could test using an LSTM layer to try and improve model performance even more. Those would be some good pieces of future work. Thank you.